In this section, we want to introduce logarithmic functions, which they may not appear initially to be, but turn out to be very closely connected to exponential functions. Logarithmic functions are functions of the form y equals, or I guess we should say f of x, to indicate that it's a function. F of x is equal to log base b of x. Just like exponential functions, log functions have a base, which is written as a subscript on that log statement. So that would be like log subscript b, a little small b there. What we have pictured below is a graph of a logarithmic function. F of x is equal to log base 2 of x. And then we also have the graph of g of x equals the square root of x. These two graphs have some similar behavior, but also some differences. We can start off with the similarities. As x approaches positive infinity, both functions are going to be headed to positive infinity. It may not be as intuitive with this graph as some others, because that rate of growth is a lot slower. But as our function, or as our x value increases, this curve for f of x is going to continue increasing. This curve for g of x is going to continue increasing. They're not shooting off to infinity, but they are going to continue to take on larger and larger function values. So as x approaches infinity, f of x will be approaching infinity. And as x approaches infinity, g of x will also be approaching infinity at a much slower rate than what we've seen with exponential or power functions. As x approaches negative infinity, now we'll see two different behaviors. Our function f of x is going to be headed down, getting closer and closer to the y-axis without ever crossing over it. So our function f of x is headed to negative infinity, meaning for the log function, we have a vertical asymptote at x equals 0. And then as x is approaching negative infinity, let me step back. That should be as x is approaching 0 from the right. We're not considering x all the way to negative infinity because that's outside the domain for these two functions. Apologize for the mistake there. As x is approaching 0 from the right-hand side, f of x will be approaching negative infinity, and g of x will be approaching 0. We can actually take that a step farther to say that g of 0 is equal to 0. So not only is the square root function approaching 0, it actually hits a function value of 0 when x is equal to 0, versus f of 0 is undefined because we have that vertical asymptote that the curve will approach but never cross over. When we talk about log functions, we have base 10 and base e logarithmic functions that have special forms or special notations that we use. For instance, a log base 10 logarithm would actually be written as just log of x. So whenever we see written in a book or written in a problem somewhere, a log without that subscript, without that base, that is generally implied to be 10. And if we have a log base e logarithm, then we would replace that log base e notation with an L and an N, which stands for natural log. I generally write that L as a cursive L just to differentiate it from looking like a 1. But lowercase l, lowercase n of x is the natural log of x. But I do want to point out one case that we need to keep in mind here. is that when we use Wolfram Alpha or other technology-based systems, this notation can vary a little bit. So for instance, with Wolfram Alpha, log base e is actually written as just log of x. We'll revisit that, reinforce that, and look at where Wolfram Alpha tells us that so that we know. But when we're using that technology or other technologies, that convention can change a little bit. Versus Wolfram Alpha would represent log base 10 of x as log base 10 of x. It just changes that naming convention a little bit. But otherwise, if we're looking at something out of our textbook or a homework problem, that log with no subscript would be assumed to be the same thing as log base 10.